Back. Types of tests. The null hypothesis H0 always states that the parameter of interest equals a specified value. So remember, H0 should have an equality. The alternate hypothesis H1 states that the parameter is less than, greater than, or simply not equal to the same value. So H1 is about inequality, less than, greater than, or simply not equal. All right. We categorize a statistical test as left-tailed, right-tailed, or two-tailed according to the alternate hypothesis. So what are these? Okay. Types of statistical tests. A statistical test is left-tailed if H1 states that the parameter is less left than the value claimed in H0. Right-tailed if H1 states that the parameter is greater than the value claimed in H0. Two-tailed if H1 states that the parameter is different from or not equal to the value claimed in H0. Okay, left-tailed, less than, right-tailed, greater than, two-tailed, not equal. In this introduction to statistical tests, we discuss tests involving a population mean mu. However, you should keep an open mind and be aware that the methods outlined apply to testing other parameters. For example, P, sigma, mu1 minus mu2, P1 minus P2, and so on. Okay. So, null hypothesis. Okay, this is just an example. Instead of mu, you could have P, sigma, whatever, right? But pretend we are talking about mu. Null hypothesis claim is about mu or historical value of mu. Mu equals some number. So the population mean is some number. That is H0. Left-tailed, mu is less than the value stated in H0. So H1 is mu less than K. Mu less than K is left-tailed. Right-tailed is H1 mu greater than K. Two-tailed, H1 is mu not equal K. All right. Hypothesis test for mu1. Given X is normal and sigma is known. So you know that X is normal and you know the value of population standard deviation. Now how do we approach hypothesis test of mu? Once you have selected the null and alternate hypotheses, how do you decide which hypothesis is likely to be valid? Data from a simple random sample and the sample test statistic together with the corresponding sampling distribution of the test statistic will help you decide. Okay, so what is it? Data from a simple random sample. Then you take the sample test statistic. Use that along with the corresponding sampling distribution. Okay, we will go through this decision process in example 2. We know that a population parameter is a numerical descriptive measurement of the entire population. So parameter pertains to the entire population. Examples of population parameters are mu, p, sigma. It is very important to remember that for a given population, the parameters are fixed values. They do not vary. Okay. So once a population is decided upon, parameters are fixed. All right. When you start looking at samples, then you get what is called statistic. They will vary depending on the sample. But parameter is fixed for the given population. Null hypothesis H0 makes a statement about a population parameter. A statistic is a numerical descriptive measurement for a sample. Examples of statistics are X bar, P hat, and S. Statistics usually vary from one sample to the next. The probability distribution of the statistic we are using is called a sampling distribution. Okay. For hypothesis testing, we take a simple random sample and compute a sample test statistic corresponding to the parameter in H0. Based on the sampling distribution of the statistic, we can assess how compatible the sample test statistic is within H0. In this section, we use hypothesis tests about the mean to introduce the concepts and vocabulary of hypothesis testing. In particular, let's suppose that X has a normal distribution with mean, mu, and standard deviation sigma. We know that X bar has a normal distribution. Because X has normal distribution, X bar, this is sampling distribution. It also has normal distribution with mean, the same mean, and standard deviation sigma over square root n, n being the sample size. Requirements. The X distribution is normal. You know the standard deviation sigma. Then X bar has a normal distribution. The standardized test statistic, standardized one, is Z. X bar minus mu over sigma over square root n. X bar is the mean of the simple random sample. Mu is the value stated in H0. N is the sample statistic. Okay. Here is an example. Rosie is an aging sheepdog in Montana who gets regular checkups from her owner, the local veterinarian. Let X be a random variable that represents Rosie's resting heart rate in beats per minute. From past experience, the vet knows that X has a normal distribution with sigma 12. So this is known and we know that X is normal. The vet checked the Merck veterinary manual and found that for dogs of this breed, mu is 115 beats per minute. Over the past 6 weeks, Rosie's heart rate, beats per minute, measured 93, 109, 110, 89, 112, 117. The sample mean X bar is 105. So they have added all this and divided by 6. The vet is concerned that Rosie's heart may be slowing. Do the data indicate that this is the case? Aha. So you see, for dogs of this breed, mu has to be 115. Whereas for our Rosie, for 6 weeks, so a sample size of 6, turns out X bar is 105. So does this say that Rosie's heart may be slowing? Solution. So first we want to establish the null and alternate hypothesis. If nothing has changed from Rosie's earlier life, then her heart rate should be nearly average. This point of view is represented by the null hypothesis. H0 is mu equal 115. Remember, H0 should have an equality, okay, an equation. The vet is concerned about Rosie's heart rate slowing. So alternate hypothesis is mu less than 115. Okay, so we are expecting mu to be so this is the alternate hypothesis we wish to test. Are the observed sample data compatible with the null hypothesis? are the 6 observations of Rosie's heart rate compatible with the null hypothesis? Okay. To answer this question, we need to know the probability of obtaining a sample mean of 105 or less from a population with true mean mu equals 150. Where did you get 105? Well, that was Rosie's heartbeat, average heartbeat rate, heart rate over 6 weeks. Okay, so we are away from 115 and we are less than 115. So the question is to find the probability of obtaining a sample mean of 105 or less. If this probability is small, we conclude mu equals 115 is not the case. Rather, mu less than 115 and Rosie's heart rate is slowing. Okay, the point is, if the probability of getting a sample mean of 105 or less is small and yet Rosie was at 105, then you have to conclude that Rosie's heart rate is slowing. Okay, so the issue is whether that probability is small or not. So what is small? How do we compute this probability? Well, you probably guessed it. We will use the sampling distribution for x bar. Compute P of x bar less than 105. So here is the sampling distribution. Mean is 115. We are at 105 or less. Well, standardize this and that gets you negative 2.04. Okay. Since x has a normal distribution, x bar also has a normal distribution for any sample size n and given sigma. So mu is 115, sigma is 12, n is 6. So x bar equals 1050 converts to standardized score negative 2.04. Okay, using this formula. Once you have that formula, notice probability of x bar less than 105 is same as probability of z value less than negative 2.04, which is 0.0207. The area in the left tail that is more extreme is called the p-value of the test. So p-value is this. So this is called the p-value. Okay. So looking at the picture, you are looking for this area, this tail. It's called p-value. Okay. Interpretation. What conclusion can be drawn? If H naught, the null hypothesis, mu is 115, is in fact true, the probability of getting a sample mean of less equals 105 is only about 2%. Where did the 2% come from? There, 0.0207. So that's 2%. 2%, 2.07%. Because this probability is small, we reject this and conclude that H1 mu less than 115, Rosie's average heart rate seems to be slowing. Have we proved H naught mu equals 115 to be false and H1 mu less than 115 to be true? No, the sample data do not prove this to be false and H1 to be true. We do say that H naught has been discredited by a small p-value. Therefore, we abandon the claim. Okay, we have not proved this to be false. We simply drop the claim and adopt the claim H1, the null hypothesis, the alternate hypothesis that mu is less than 115. Okay, we'll come to the next topic in our next videos. Until then,